The question that I have is, could you do an example on finding cable tensions? Let's go ahead and do this problem that we have used in the discussions in some of the earlier videos. We have a mass of 50 kilogram being held in space by a cable system shown in the picture. Our question is to find the tensions in the cables. So the first step is to identify particles that we would use in the analysis. Here, these will be particle A, which connects the three cables, and particle D, which is the mass of 50 kilogram. Obviously, implicit here is the assumption that the ring A and the mass D can be approximated as particles, right? Remember, particles are mathematically represented by points, so we don't consider the dimensions of the bodies. The second step is to complete the free body diagram for the particles that we have identified for the analysis. So in this example, they are particles A and D, and we have completed the free body diagrams right in the main problem picture. If you recall, for this problem, we have discussed the details in some of the previous videos. If you haven't watched those videos yet, I recommend that you go back and watch them before you continue here. The third step is to use equilibrium equations to solve for the unknowns. Now remember, this is a 2D problem, right? A problem involving coplanar forces. And therefore, we can only write down two equilibrium equations for a given free body diagram. And therefore, we need to start from a free body diagram that has at most two unknowns, right? In this example is clearly the free body diagram for particle D. Particle A, on the other hand, has three unknowns, TAC, TAB, and TAD, and therefore that has to wait. So I write down an equilibrium equations in the vertical direction, the y direction, and this is my equation. TAD is the tension acting vertically up, and W, which is 490.5 Newton, is a force acting vertically down. So that goes in as a negative term in this equation. Those are the only two forces acting on this particle, and we have considered both of them, and therefore you set this to 0, right? And from that we get TAD equal 490.5 Newton. So I'm going to write that over here for the tension TAD acting on particle A before I consider particle A, so that I don't think of that as a unknown anymore, because we have solved for that unknown already. Now the number of unknowns for the free body diagram at particle A has reduced from 3 to 2, and therefore theoretically we should be able to find the two unknowns, because we can write down two equations. So let's go ahead and do that. So here are the two equilibrium equations I have written down for the free body diagram of particle A. Here is the equation in the x direction, here is the equation in the y direction, horizontal and vertical respectively. There are three forces involved in this free body diagram. Remember, you have to consider all of them, and if one of them is not going to show up, you can eliminate them, but you have to consider each and every one of the forces acting on the free body diagram. So in the equation for the horizontal equilibrium, you can see the force TAD, which is 490.5 Newton, is not going to show up because it's perfectly vertical, and therefore it does not have a horizontal component. The horizontal component of TAC is TAC cosine 30, right? And the direction of that horizontal component is in the positive x direction, and therefore it goes in as a positive term in equation number 1. And the horizontal component of TAB is TAB cosine 45, and then that goes in as a negative term because its direction is pointed in the negative x axis. Remember, I'm not really drawing the x and y axis explicitly here, but it's understood by default. Your x-axis is the horizontal axis going to the right, and the y-axis is the vertical axis going vertically up. In the vertical equilibrium equation, all three of the forces are going to show up. The vertical component of TAC is TAC sine 30, and that goes in as a positive term. The vertical component of TAB is TAB sine 45, and the arrow on that vertical component is also directed vertically up, so that goes in as a positive term there. 490.5 is already a vertical force, and therefore that goes in as is, but with the negative sign in front of that because the arrow on that is vertically down. That's it. We have considered all three forces, so now you can set it to 0. We have two equations, two unknowns, so we have to solve for the unknowns by considering these two equations simultaneously. There are many ways to solve equations like these. This is what I'm going to do. I'm going to find TAC from equation number 1 in terms of TAB. And then I'm going to bring that and substitute into equation number 2. Then the equation number 2 will be just in terms of TAB, just one unknown, and we can go ahead and solve for that. Once we do, then we can go back to this equation that expresses TAC in terms of TAB and find a value for TAC. So let's go ahead and do that. So here are the details. From equation 1, I find that TAC equals 0.816 TAB. Substituting that into equation number 2, I get a value of 440 Newton for TAB. So the details are pretty easy to follow. I'll let you follow. So I brought a couple of steps from the previous slide here. Now substitute the value of TAB into equation number 3. I get a value of 359 Newton for TAC. That's it.